The rapidly expanding field of machine learning increasingly affects our daily lives. Machine learning algorithms are now outperforming humans at tasks like face, object, and optical character recognition, and even passing milestones like outperforming expert human players at the board game Go. As the usefulness of machine learning expands, so must our trust in its accuracy. We depend on it for driving, piloting, computer security, financial, medical, and legal applications. Malicious input is a real threat. Machine learning is the subset of AI which aims to reproduce some behavior seen through training data rather than through explicitly programmed rules. In this context, accuracy is the proportion of inputs labeled correctly from a previously unseen dataset. While, traditionally, this set is a subset of training data, or the closest possible thing to training data, in practice there are often relevant differences. Even incidental changes like the type of camera used to take a picture can reduce the model accuracy. We are going to examine the digital generation of these changes to attack machine learning models with adversarial input and the defenses to these attacks.
This article focuses on machine learning algorithms that perform classification, learning and mapping from an input x to a discrete variable y, where y represents the identity of the class. As a unifying example, we discuss road sign image recognition. Different values of y correspond to different types of road signs, such as stop signs, yield signs, and speed limit signs. Examples of input images and expected outputs are shown in the image here. Though we focus on image classification in this article, the principles of adversarial machine learning apply to much more general artificial intelligence paradigms, such as reinforcement learning. Machine learning models are commonly deployed as part of a data pipeline. Inputs are pre-processed and fed into the trained model. The output determines the state or action to be taken by the system. The example shown here, relating to the earlier example of a traffic sign classifier, could be deployed in an autonomous vehicle. A camera on the vehicle would capture and process images. The images would then be fed to a classifier trained for detecting road signs. The class predicted by the machine learning model could then be used to decide what action should be taken by the vehicle, such as come to a stop if the traffic sign is classified as a stop sign. Most machine learning models are designed, at least partially, based on the assumption that the data at test time is drawn from the same distribution as the training data, an assumption that is often violated. It is common for the accuracy of the model to degrade due to some relatively benign change in the distribution of test data. For example, if a different camera is used at the test time from the one used to collect the training images, the training model might not work well on the test images. This phenomenon can be exploited by adversaries capable of manipulating inputs before they are presented to the machine learning model. In the earlier example of an autonomous vehicle, an adversary capable of crafting stop signs classified as yield signs may cause the autonomous vehicle to disobey traffic laws and potentially cause an accident. This is demonstrated by the image here showing modified stop signs from a 2018 paper by Kevin et al. Robust physical world attacks on deep learning visual classification. These stop signs with minor alterations were shown to deceive autonomous vehicles effectively. As is common in modeling security of any domain, the domain of adversaries against machine learning systems can be structured around a taxonomy of capabilities and goals. As reflected in the graph shown here, the adversary's strength is characterized by its ability to access the model's architecture, parameter values, and training data. An adversary with access to the model architecture and parameter values is capable of reproducing the targeted system on its own machine and thus operates in a white box scenario. In addition to the different degrees of knowledge about the model internals, adversaries may also be distinguished by their ability to submit inputs directly to the machine learning model or indirectly through the data pipeline as shown in the previous example before processing.
When constructing an adversarial input, most methods start with a valid input vector x and perturb it to make a new vector x star that meets their functional and detection goals. Functional goals concern the adversary's intentions directly, for instance, whether a piece of malware executes successfully or whether a targeted attack on a classifier causes the correct misclassification. Detection goals are about getting past whatever defenses the machine learner is using, including fooling human inspectors. In practice, this means limiting the size and scope of the perturbation. Two norms which control the scope of perturbations are the L0 and L-infinite norms. The L0 norm limits the scope of the perturbation to as few elements as possible, but allows any changes to those elements. The L-infinite norm allows any element to be modified, but forces only very small changes to be made. There are several ways to manage trade-offs between functional and detection goals. One is to choose a deviation budget and find the maximum error achievable with it. Another finds the minimum deviation that will allow the attack to meet its functional goals. Both approaches are often intractable, so gradient-based approximations of them are used instead. Let's introduce three leading gradient-based methods: limited memory BFGS methods, fast gradient sign methods, and Jacobian-based saliency map attacks. First published in 2013 by Szegedy et al., the LBFGS approach, or limited memory, Broyden, Fletcher, Goldfarb, Shano approach, was the first to successfully cause the misclassification of an image by adding a perturbation undetectable to humans. The approach is still developing, with Carlini and Wagner developing successful variants that minimize detection and bypass contemporary defensive techniques. These methods are costly, but running them with fewer iterations can reduce this cost in exchange for a reduced success rate. Introduced by Goodfellow et al. In 2015, the FGSM, or fast gradient sign method, is a cheap source of multiple viable perturbations at the cost of generating larger, more detectable perturbations. It seeks to maximize the error generated by modifying a limited number of inputs. That is, it follows the L0 norm. As the error generation function can be hard to discover, a first-order Taylor series approximation is used instead, treating the error function as roughly linear. This exploits the local sign of the gradient in each dimension, which is much more accessible. In 2016, Papernot et al. Introduced Jacobian-based saliency map attacks. While LBFGS attacks and FGSM attacks are untargeted, JSMAs can choose a target class to misdirect an input into. Starting with the Jacobian of the error function, they construct a saliency map, a measure of the importance of each element of X to the identification of an input as the targeted class. Components of X are modified in order of decreasing saliency until a misclassification into the correct class results, a variation of the L0 norm. The image shows a JSMA attacking a deep neural network used for handwriting analysis. As we have previously mentioned, each method has strengths and weaknesses, some of which are shown in this table. In summary, LBFGS attacks are high-quality, high-cost, untargeted attacks. JSMAs are similar, but targeted and easier to defend against, and FGSM attacks are cheaper, untargeted attacks with lower success rates in most circumstances.
In the previous sections, we've already discussed the white box techniques that can be used by adversaries, but are these really realistic attacks? An easy countermeasure to them would be for the developer of the machine learning system to not make their model and parameters public. Simple enough, but a drive for open source programs will always exist, so this does not fix all situations. So, if we now assume the attacker does not have access to the model and parameters, what are his options? If the attacker has access to training data, then they can simply create their own model using the same data. It's highly likely that the same adversarial inputs that will produce an incorrect result on the substitution model will also trip up the model being attacked. The biggest challenge for the attacker is knowing what type of model to train. This may be able to be found by social engineering or guesswork. More on this later. If the existing model is able to be tested in some way, we refer to this as an oracle. We can continuously ask it questions of inputs and see what the response is. By collating these together, we gather a training set that again we can build and train a model on to then explore the decision boundaries. The attacker could of course directly apply their white box manipulation techniques to the oracle, but it's perfectly possible the model would either learn from these or the malicious activity could be detected. The analogy used in the paper is that of machine learning to recognize road signs. Here we see an example of an algorithm being used to extract training data from an oracle. By algorithmically modifying the inputs, adversarial substitutes can be detected. but again, this may be detected as malicious activity. Activity is less likely to be detected at a low frequency or without the modifications. One of the biggest issues the attacker faces when reconstructing the model is knowing exactly which architecture is used. For example, how has the programmer clustered the data? The attacker can use any pre-existing knowledge to guess this, but may have to resort to creating multiple models and seeing which best matches the model that they're substituting for. If creating one model is expensive, creating many could be much more so. However, adversaries in one model can often translate to another model also. Finding adversaries from the input with respect to the output is effectively an optimization problem. As such, a genetic algorithm could be used to find a solution. Firstly, a range of input solutions is proposed for testing. Then, the best fitting inputs are modified to make a new generation. Test and repeat until an adversary is found. A crossover of two well-fitting solutions and a mutation could be used. This or any other technique's effectiveness usually depends on the original model used. However, adversarial examples found for one model may also apply to other models. It's generally in the defender's interest to withhold as much information about the model as possible.
Given the existence of adversarial samples, an important question is, what can be done to defend models against them? The defensive property of a machine learning system in this context is called robustness against adversarial samples. We now explore several known defenses categorized into three classes: model training, input validation, and architectural changes. Adversarial training seeks to improve the generalization of a model when presented with adversarial samples at test time by proactively generating adversarial samples as part of the training procedure. Although it was not previously practical due to the high computational cost of generating adversarial samples, the fast gradient sign method made it computationally efficient to continuously generate new adversarial examples every time the model parameters change during the training process. The image here shows handwritten figures generated during the adversarial process. The model is then trained to assign the same label to the adversarial example as the original example. Defensive distillation smooths the model's decision service in adversarial directions that could be exploited by the adversary. Distillation is a training procedure whereby one model is trained to predict the probabilities output by another model that was trained earlier. It may seem counterintuitive to train one model to predict the output of another model with the same architecture. The reason it works is because the first model is trained with hard labels, for example, an image with 100% probability that it contains a stop sign rather than a yield sign. And the second model is then provided with soft labels, for example, an image with a 95% probability of a stop sign rather than a yield sign. Both adversarial training and defensive distillation suffer from limitations, however. They are generally effective against inexpensive white box attacks, but can be broken using black box attacks or computationally expensive attacks based on iterative optimization. These two strategies are good examples of defenses that perform gradient masking. Perhaps the most obvious defense is to validate the input before it is given to the model and possibly pre-process it to remove potentially adversarial changes. In many application domains, there are verifiable properties of inputs that should never be violated in practice. For example, an input image from a camera sensor can be checked for realism. There are certain properties of cameras and light that ensure certain pixel neighborhoods, such as neighbor pixels with exceptionally high contrast, never occur. This is demonstrated in the image here, showing a regular pixel neighborhood on the left and a possibly adversarial input on the right. These defenses are limited in that they are highly domain independent and subject to environmental factors. It is also possible to defend against adversarial samples by altering the structure of the machine learning system. Highly nonlinear machine learning models are more robust to adversarial examples, but also more difficult to train and generally do not perform well in a baseline non-adversarial setting.
In summary, the biggest security issue with traditional machine learning models is that adversarial inputs are not considered. For some applications, such as computer security, this could be a big issue. Various verification methods have been proposed. Basically, developers must train their networks on adversaries for robustness. For security applications, we need to guarantee an upper bound of failure. By taking a white hatting approach and anticipating these adversarial methods, models can be better suited to deal with inputs. The boundaries effectively need to be moved away from the classification points to allow for variance in inputs without reclassification. This could of course cause issues with the overall solution. The common Cleverhands benchmark looks at various types of adversarial inputs, but the fast-moving pace of machine learning means a better method may soon be available to the adversary, who can utilise this to manipulate the old model. Due to the complexity of machine learning, it's generally advantageous for attackers because it's hard for the defenders to deal with all possibilities. The huge input space makes many pessimistic that machine learning can ever be fully defended against adversaries.